this tutorial, I am going to show you how you can call variants using BCFTOOLS. In order for you to follow this tutorial, you need to make sure you have a Unix-like operating system, i.e. Linux or macOS. In addition, you should have Anaconda installed on that PC. Anaconda will be used to install the tools and packages you will use for this exercise. I have a separate tutorial that shows you how to install Anaconda, so just watch that video to set up Anaconda on your system. The link to that video is in the description box. Now for this tutorial, here is the workflow we will use. We are first going to download some sequence reads. We are going to use paired end reads. Okay, we will just use one sample. And so these reads will be trimmed as a form of quality control, and then the trim reads will be mapped to a reference genome. So after mapping, a SAM file will be generated. This SAM file will be converted to a BAM file, and then the BAM file will be sorted. After that, we are going to use BCFTOOLS mpileup command to generate the coverage information for all the bases. After that, we are going to call the variants using BCFTOOLS, and then we are going to do some post-vcf analysis. So this is the workflow we are going to use. And so without further ado, let's start the exercise. The first thing to do is to install the software we need. I will use Anaconda to do this. Anaconda does a great job of installing tools, so that is why I like using it. So I will just proceed. So I will need to add channels. So this is what I will do. I will say conda config add channels, and then I will specify the name of the channel. So the first one we are adding is conda forge, so I have it here. Let's add a second channel, which is conda config add channels, and that is bioconda. So that is the second channel. You can also list the channels you added, so I will just say conda config show channels. We have the two channels we added here. The default channel comes packaged with conda, so we will leave it as it is. The next thing we will do is to create an environment and install the tools we need in that environment. So we will do both at the same time. So we will say conda creates -n, and then we specify the environment name. So it's called variants. Let's just use the word variants. So let's say variants. And then we will indicate or list the tools we need. So we are going to use BWA. We are going to use BCFTOOLS. We are going to use samtools. We will use sickle. We will also use Python, and then we will use BioPython. So BioPython is a Python library. Okay, so these are the software or tools we will use for this exercise. So let's run this command to install them. Okay, so we need to confirm the installation. So I'll type Y, and then I'll run this command. And so conda will download the tools, extract, and then install them. And please take note that sometimes the process might take some time, so you just need to be patient for it. Now it's done, so you will have this information here telling you how to activate the environment. So that is what we have here. So let's clear the screen and then just continue. Okay, now we will just test the tools. We just want to make sure everything is okay. So to test the tools, we need to first activate the environment. So with conda, if you want to run the tools, you first have to activate the environment which has the tools, and then you can just run them. So we will need to activate. So I'll say conda activate, and then I'll indicate the environment name, which is variants. And so after a successful activation, you have the name appearing on the terminal. So that is what we have here. So let's test some of the tools. Let's say BWA. It's fine. Let's just type BCFTOOLS. It's also fine. So I assume that the other tools have also been installed successfully. So we have it there. So now let's clear the screen and proceed. The next thing to do is to download the example data. We are going to use a paired end sequence data. So this data was generated and made available by authors of this paper. And so with this paper, they sequenced a mycobacterium mulstrans isolates, and the sequencing was done using two platforms, Illumina and then Nanopore. But we are going to use the Illumina reads for this exercise. So the Illumina reads and Nanopore, both reads are available on the SRA database. So with the Illumina reads, you can use this accession number to download or get access to the data. So that's what we'll do. Let's go and then just download the Illumina read. So there is a page, and I will leave the link to this page in the description box for you. So just use that to visit the page. So when you are here, just check these tabs here, click on the data access. This one here, click on it, and then you have this appearing. The data is available on different servers, but we will use the one on the EBI server. So we have read 1 and then read 2 here. So let's download it. So to download it, if you are using the browser, you can just click it, and once you click it, you'll be asked to save the file, just as it's appearing. So once you have it this way, you can just click OK and then just save it. But if you are working on a remote server, then using this approach may not work. So you have to get the download link and then just use that. So that is what we'll use. You can also use the SRA toolkit to download. I've made a tutorial on that. You can just check it out. But for now, we'll just use a direct link here. We'll do a direct download. Okay, so let's start with the read 1, which is the forward. So we'll just get a link here. This link, we'll just copy it, and then we'll go to the terminal to download it. So let's go to the terminal and then download that. So we are now here. So here, what I'll do first is to create a directory where I'll be working in. So let me just create. So I'll say make that projects, and then I'll cd to that directory, and then I'll start my work. So I'll begin with the downloading of the R1, which is the read 1. So I'll use wget, and then I'll supply it with a download link like this. That is what I'm going to do. Okay, so I'll have it here, and then I'll just download it. So let me just download it here. It's a small file, so it wouldn't take much time to download. So let's wait whilst download is being done. Okay, so we have the read 1 downloaded. Let's do an ls to check it. So it is here. Now let's download the read 2. That is the reverse. So let's go back and get the download link, which is also here. So we have the link here. We'll just copy it and then go and then just get it on the terminal. So let's open the terminal now to download that one as well. So the same we get, and then we just supply it with a link, and then we download it. Okay, so we have the read 2 also downloaded. Let's do an ls, and you'll find it there. So we have both reads available for us. So now let's proceed. Let's clear the screen and just proceed. The next thing to do is to download the reference genome. If you take a look at the paper, we are dealing with a mycobacterium mulstrans isolate. With mycobacterium mulstrans, the reference genome is the AGY99 strain. This genome is available on the NCBI database. And there's a page. I will leave the link to this page in the description box. I will also give you 2 ways you can use to download the genome. We will use the FASTA format. So on the browser, just come to send to, and then it's on the right side. Just come to send to, click on it. The send to button, just click on it. Make sure complete record is checked, When you come to choose destination, select file. When you come to the format, select FASTA, and then click on the create file. So this will bring up this pop-up here, which indicates or prompts you to download it. So I'll just save, and then I'll just give it a name. I'll say AGY99.FASTA. So this will be my name for the reference genome. Now, if you're working on a remote server, then you may not have access to a browser. Okay, so because you don't have access to a browser, that means you have to use another approach to download the genome. And that is what we are going to use. So I'll show you how you can also download this same data, this reference genome here, using Python. So let's go back to the terminal and I'll show you that. So when you're on the terminal, let's just type Python. We have already installed it, so I'll just go straight to the points. If you have already obtained the reference genome, then you can skip this section. So take note. But if you want to learn more, why not? Just follow my lead. So we have Python. We also have the libraries we need, and so what we will do is to import them. So we will say from bio import entrance. So we are using the BioPython package. So with the BioPython package, we have the entrance and then the sickle models. So these are the two models we will use to get the genome. With entrance, you also need to supply it with your email address. So we say entrance.email equals bioinformaticscoach@bioinfo.com. So it should be in quotes. This is a strange data type. So if you start with single quotes, it should end with single. If it's double, it ends with double. So we have the email also added. Now we can download the genome. So we have this command here. We say handle equals entrance.efetch. We are fetching from the web. And then we give this information here. We have DB, which is new call. Let's spell it correctly. So we have it this way. Then the ID, which is the accession ID. Let's go back. So this is accession ID. So you can just use that. I'll put it in the description box as well. So you need that information. So we say ID equals CP000325.1. That is the accession ID. It should also be in quotes. They are strange data types. Then the rest type here will be FASTA. We want the FASTA formats. Red mode here, we will just say text. So we have it this way. So now we can run this to download the data. Okay, so the efetch command has been executed. So what we will do next is to put our data in shape so that we can export it. And so we will say record equals sickio.read. And then we indicate the objects. So that is handle. And then we indicate the format we want, which is FASTA. So now we can run this command. Okay, so now the data is ready to be exported. So we say sickio.write. That is how we are going to export this to a file. And then we indicate our record, and then we also indicate the output name, which is AGY99.FASTA. And then we indicate the format, which is FASTA. Then we run this. So now it has been done. The one here is just telling us the number of sequences that were written to a file. So now it's there. Let's quit Python. And then we can now do an ls to check. And you see that we have it also there. So that's how we do it. Let's just do a quick exploration here. Let's just say head -n5 just to get it here. Okay, so we have the reference genome here, which is cool for us. So, I mean, we are good to go. So, a good job to everyone. Now we can proceed. So, let's clear the screen and then just continue. Okay, so we have what we need for the start. Let's do an ls to check the files. So, we have them here. Now, when you are dealing with raw reads like this, it is important to perform quality control. Quality control will help you to know the quality distribution of the bases. You can use tools like fastqc to do that. Fastqc, for example, will do some analysis and then generate plots and a visualization that you can use to check the quality of the bases. And so it's important you do that. In addition to the inspection by fastqc, you can also do trimming. So trimming helps to remove adapters. It also helps to remove reads of low quality and those that are bad. So in general, trimming helps to improve the quality of the reads. Okay, it's not all the time, but in general, that's what it does. So what can be done is that you can check the quality of the reads before trimming, and then after trimming, you can also check and decide which of them is of a better quality, and then use that for the analysis. So let's proceed. So for this tutorial, I'll just do a trimming, and then I'll do the trimming with the assumption that the trimming improves the quality of the reads. So that is what I'll do. I'll use the tool called sickle. So let me just type sickle. We have installed it. If you use the instructions I just demonstrated, then you have already installed sickle. So let's type this, and then you have them there. So with sickle, you can run in the paired end mode, which is P, or in the SC mode, which is single end mode. So because we are dealing with paired end reads, we will use the PE mode. So let's look at how sickle is used in the PE mode. So let's type sickle PE. So you have the information here. So you can just read about the information here that tells you how to use sickle and then the options available for it. So I will just proceed with the trimming. So just try and then just read about it. So let's clear the screen and then just continue. So we will trim the reads. So that's how we are going to do it. Let's type sickle first. And then let's type P. And then we will just indicate the forward reads with -F. So the name is P7741R1. That is read 1. Now, with the reverse, we use -R. So let's also indicate the name. So that will be P7741R2. And then we also indicate the quality type, which is -T. We will use Sanga. There are other formats like Solexa and then others, but just check the sickle documentation page and then you will see the available options there. So we have the quality type. Let's look at the other aspects. We have -Q20. So -Q here tells sickle to trim reads that have this quality, that have qualities below 20. And then we will use -L to trim reads that have lengths below 20. And then we will also indicate -G. So -G here tells sickle to compress the files that will be generated. So we have this information. Now let's specify the output files, the name of the output files. So we have -O. Okay, -O is for the trimmed forward reads. So let's just name them as trimmed R1.fastkill.gz. And then let's look at -P, which is for the trimmed reverse reads. So the same trimmed, but this time R2.fastkill.gz. Let's type it well. And then we also indicate -S for single or unpaired reads. So we say -S. Let's name that one trimmed _s.fastkill.gz. So we have that also here. Okay, so we have all the information we need. And so we are going to run sickle now. Okay, since there was a typo here, so let me just correct it. So, okay, so I think, yeah, perfect. So now we have them ready. So let's run sickle now. Okay, so now trimming has been done. And so you have this information popping up. Okay, so let's do an ls and just check the files out. So ls and then you see the files there. So we have the files. We have trimmed R1, trimmed R2, and then trimmed S. So these are the files that have been generated by sickle. So now we are ready. Let's proceed to the next phase of the exercise. So let's clear the screen first. Okay, so now we can proceed to the next phase of the exercise. The next thing we will do is to perform genome mapping, and we do this by aligning the reads to a reference genome. We already have our reference genome here, and we also have our reads. We are going to use a trimmed reads. The purpose of genome mapping is to identify regions or locations in the reference genome where the reads map uniquely to, or where the reads correspond to, or where there is the best match for the reads. And so that is what we are going to do. The information we get from the genome mapping will then be used by the variant callers to identify variants. And then we also get to know the position or the region where these variants can be identified. So that's what you need to know. There are lots of tools available for genome mapping, but we are going to use the Burroughs Wheeler Aligner. So this is the page in case you want to read about this tool. So just take it. I will leave the link to this page in the description box as well. So let's proceed. So we are back. Now, before we do the mapping, it is important to also do an indexing of the reference genome. Indexing helps programs to do a faster lookup of the sequence. And so that is what we will do first. So we are going to use BWA for the indexing as well. So just type BWA. It's already installed. If you follow the instructions that I displayed earlier on for the installation, then BWA is already installed. So just type BWA and then you have the options here. So that's what you need to do. Now let's do the indexing. So before we do the indexing, let's move this file to a different directory. We just want to organize the files. The indexing will also generate some files, so we just want to separate them. So let's create a directory. So we have makedir ref, and then let's move the file there. So mv agy99.fasta, and then we move to the directory. So do an ls, and then you see that the file is no longer in the working directory, but the file can be found in the ref directory. So we have it here. Okay, so let's proceed. So we will now do the indexing. So we say bwa index, and then we specify the path to the file. So ref agy99.fasta. So let's run this. Okay, so indexing has been done. There's a small genome, so indexing will be fast. So that is what we have. So now if we do an ls in the ref directory, you see that we have some files generated in addition to the fasta file. So these are all files that will be used by BWA for the mapping. So let's proceed. Now let's clear the screen and just proceed. The next thing we will do is to perform the genome mapping itself. So we will use BWA to do that as well. So let's just check the files once again and then proceed. So we will use the forward and the reverse. These are the which we use. This one, we are not going to use it. We usually use these two. So that is what we will do. So let's proceed. So we will say BWA mem, and then we indicate the number of threads. That's T. If you are working on a server or you are working on a high-end PC, you can increase the number of threads if you have multiple, or if you have a lot of CPUs. So just take note. So the higher the number of threads, the faster BWA will run. So take note of that. Now let's specify the reference genome. So we use the paths. So we say ref/agy99.fasta. The other files, we don't indicate them. So BWA will automatically detect them. Now we continue by specifying the reads. So we specify the read 1 first, that is the forward, and then we add the read 2, which is the reverse. So we say trimmed r1.fastq.gz and then trimmed r2.fastq.gz. After that, we specify the output file, the name of the output file. We are going to generate a SAM file, which is the sequence alignment map. So let's say output.sum. Okay, I think, yeah, some of the text just came here, but it's fine. So that's what we need to do. So now we can run this command. And so BWA will start the mapping. So let's wait whilst that is done. And let me also say that mapping is a computationally expensive process. Okay, so usually mapping is done with high-end PCs or on a server, okay, with a lot of costs. So take note. So if you are dealing with a large genome, then it's also advisable you use a high-end PC for this. And if you are dealing with multiple samples, all the more reason why you have to use a server or an HPC to do these kinds of stuff. So let's wait whilst the mapping is being done. Okay, so the mapping has been done for us. So let's proceed. So let's clear the screen. So do an ls, and then you see that the SAM file has been generated. Now the SAM file is large. Okay, SAM files are usually large. And so what we do is to convert the SAM files to BAM files. So BAM files are compressed files. Okay, they are compressed files for this. They are also binary and they have a smaller size. So we just want to save some space. So to convert the SAM file to a BAM file, we say samtools. We are going to use samtools. So this is also one of the tools we installed. So that is what we are going to use. So samtools, and then we say view -s-b, and then we specify the input file, which is the output.sum, and then we specify the output file, which is output.bam. So we have the input file here and then the output file. So that is what you need to know. Now we can run this. So let's wait whilst samtools does its work. Okay, so the file has been converted. So do an ls and you see that we have a BAM file here. Okay, so let's just check the sizes just to confirm. So let's check the size for the BAM file first. So it's 92 MB. Let's check that for the SAM file. And then you see the size here. So that's what I'm talking about. So that's why we normally convert to BAM and then use that one, because that one occupies a smaller space. Okay, so let's proceed. So now we have this. The next thing we'll do is to sort the BAM file. And some variant callers require BAM files which are sorted by coordinates. Okay, so we are going to sort this particular file here. So to sort the BAM file, we say samtools sort -o to indicate the output file. So let's name it outputs.sorted.bam. And then we indicate the input file, which is the outputs.bam. So outputs.bam, that will be the input file. Okay, so now we can sort. So let's wait whilst that is done. Okay, so we have it done for us. So do an ls and you see a third file generated here. So there's a sorted BAM file. And this is what we will use for the variants calling. Now, these commands are used, okay? The commands are used for the mapping and then the conversion to BAM file and then also sorting. We can combine all these commands into a single line. Okay, so that is the beauty of Linux. So I'll show you that approach as well. I think sometimes that approach is faster than just doing them individually. So let me show you that one as well. So let's first remove these files because we will not need them anyway. So let's remove them. Outputs.bam. We also have outputs.sum. And we also have outputs.sorted.bam. We are going to remove them. Okay, so now let me show you the one-liner command to do this thing. So we say bwa mem-t, and then we indicate the number of threads again. We specify the reference genome just as we did. We indicate our reads forward and then the reverse. And then we issue a pipe command. And then we call samtools. And then we say sort. And then we say -o. Okay, that is what we do here. And then we indicate the output file. So this time we even skip the conversion of the sum file itself. We just move straight to the sort one. So we say outputs.sorted.bam. And then we indicate dash. So the dash here refers to what will be generated from the first command here. Okay, the mapping command here. So that is what this dash will do. So that means we are feeding the file, okay, or the output directly to the samtools. So that is what we do here. So let's run this command. Okay, so it has been done for us, so we can proceed. And so you see the file here. Okay, so this is what we are going to use. Okay, so we are gradually moving on, and I will say good job for coming this far, because we are getting to the exciting part of this tutorial. So let's proceed. Let's just continue from there. Now, whenever you perform a genome mapping, it is important to get the statistics of the mapping. The statistics will help you to know how well the reads map to the reference genome. So, and that's what you need to know. We are going to use some tools to do these statistics. It will compute and then get them for us. So we will use the samtools flag start command. So there's the page in case you want to read about this particular command. So I'll leave the link to this page in the description box. Now back to our exercise. So this is how we get the statistics. So we say samtools flag starts. And then we also specify the sorted BAM file, which is here. So we have it this way, and then we can run this command. So once you run it, you have some information displayed for us. Okay, so we have this information here. Now with this tutorial, we are going to focus on just two of the values. This one here. Okay, so this value here indicates the total number of reads in the FASTQ files that we used. So that is what you need to know. And then we also look at this number here, which is the number for the number of reads that map to the reference genome. So in terms of percentage, we have 88.71%. So 88.71% of the reads mapped to the reference genome. So these are things you always need to look out for, because it will help you to know how well the mapping was done, and then also help you to determine the next course of action. So with this one here, majority of the reads mapped, and so the reads that did not map, one possible cause will be that these are reads from other organisms. So it's likely, it could be a likely cause. There may be other causes, but this is one of the causes. So let's proceed. So these are the two things. Now with the flag starts, you can just read about it and then just look at how you can interpret these other ones to us. So, but there are lots of forums that do that. So let's not waste time here. We'll just proceed to the next activity. So with this information here, you can also save to a text file. Maybe you want to make reference to it later on. You can just save it. Now it's just being printed for us on the screen. So to just save it, you can use this here, the same command, and we just direct to a text file. So let's just say mapping stats.txt. So this will save it for us. So do an ls and you see the file here. So the file here, you can just display it and then you have it there. So that's how you get it. So these are things that you need to do. Okay, so now we will proceed. The next thing we are going to do is what we call the mpileup. Okay, so we are going to use BCFTOOls to do the mpileup. So the mpileup is used to generate coverage information for the bases, okay, that we have mapped. Okay, so this information is used by BCFTOOls to calculate the genotype likelihood. Okay, so after that, we now do the variant calling itself. So let's proceed. So let me also show you the page in case you want to read about BCFTOOls. I think it should be here. I'll leave the link in the description box. So just check the mpileup and look at the options available for it. So let's proceed. So let's start. So we will say BCFTOOls. Let's just display the files again here. We need a sorted BAM file. So we will say BCFTOOls. We say mpileup -o, that is B. We need the output to be in the BCF format. And then we also indicate -o for the output file. So let's say raw.bcf. And then we also need to indicate the ref. Okay, that's the reference genome. So that is -f. And then we indicate ref/AGY. We need the 4 parts. So that is what we are going to use here. So we need that information. So we use the -f for that. And then we also need threads. So you see threads. You can decide to leave it, but you can also add it and then just speed up your work. So let's use 8. And then here you can also do some filtering. So -kill can be used to exclude bases, okay, that have qualities lower than a particular threshold. So let's say we want to remove or exclude bases with qualities lower or below 20. We can say -kill, that's the lowercase q, and then indicate the 20 here. So that will remove or exclude bases with qualities lower than 20. Now if you want to exclude reads that have a particular mapping quality, you can use the -kill here. So let's say we have -kill 30. Then this means that BCFTOOls should exclude reads whose mapping quality is below or below 30. That is what this means. So once we have this, we also need to specify the input file, which is the sorted BAM file. So that will be outputs.sorted.bam. So that is what we need here. So once we have this, we can run and get a pileup information. Okay, so pileup has been done for us. So we have just one sample. That is why we have this here. Okay, so if you have multiple samples, you can just check the documentation and look at how that can also be done. Okay, so now we have the pileup done for us. So do an ls and you will see the file there, which is the raw.bcf. So this is what we will use to call the variants. So we still use BCFTOOls to call the variants, and so we will say BCFTOOls, and then we say call, and then we indicate the ploidy option. So the ploidy option is used to tell BCFTOOls whether we are dealing with haploid organisms or diploid. So it's important you specify that. So because we are dealing with a bacterial genome, we are going to use a ploidy of 1 because this haploid. So we have 1 here. And then we also indicate -m. So -m here allows for the discovery of multi-allelic and then rare variants. So that's why we have this here. We also have -vin to output just the variant sites. That is what we need. And then we also have -o for the output file. So let's just say variance.raw.vcf. Okay, so we will output it in the VCF format, and then we indicate the input file, which is the raw.bcf. So we have that also here. And so that's what we need. Again, if you want to get more information about the BCFTOOLS call command, you can just go to that page. I'll leave the link to this page in the description box. So just go to the BCFTOOLS page and just read about that. So now we have everything we need, so we can just run this command to call the variants. Okay, so variant calling is being done now. It has been done for us quickly. So do an ls, and then you see the file here, which is this one here, variance.raw.vcf. Okay, so I named it variant.raw.vcf because normally if you call them, you also need to do some filtering, okay, so that you can get your final variants. So that's what you need to know. So with the filtering aspects, these are things I'll cover in other tutorials. I currently have a playlist for post-vcf or for handling VCF. So that playlist, I'll make another tutorial on how to filter variants, or how to filter the VCF files. Okay, so the filtering option or the filtering aspect of this variant calling will be done in another video. Okay, so now we have the variants, okay, here. Now, once you have this VCF file, then it's time for what I call the post-VCF, where we handle the VCF file and just manipulate it and get some information and do some analysis. So that is the exploration stage. So here I'll just take you through a few of them, and you can check my playlists on the handling of VCF files, where I cover tutorials on what to do after calling the variants to generate your VCF file. So just check that out. I will leave that playlist at the end of this video. So let's do the exploration. So we will look at the number of variants that were identified. So let's just count them. So we can say grep-v-c, and then we indicate our pattern here. I have already covered a separate tutorial on counting of variants in Linux, so check that to get full explanation of these codes. So I'll leave the link in the description box. So here's the pattern I'll call, and I'll specify the VCF file, which is variants.raw.vcf. That's what I do. Okay, so I have it here. So once I have this, I can just run this. And then I have the number of variants to be what? 32682. 32,682. So it's good. So there's something you can just look at. You can also check the variant types and then just count them. For now, we'll just count just the two common types. I don't want to use the word common, but I'll just say it like that. So I'll just count two variant types, the SNPs and then the indels. So to count, let's start with the SNPs. To count, we say BCFTOOLS view-v, and then we say SNPs, and then we specify the VCF file, so which is variants.raw.vcf, and then we can count. So then we just issue the pipe, and then we can just add these commands here, where we count and find the patterns. So that's what grep-v-c, and we indicate our pattern here. So this will give us the number of SNPs, or the number of variants that are SNPs. We can also count indels. So the same command here, but this time we change this option here to indels. So this will give us the number of indels. So we have that also here. Okay, so these are things you can just do to explore your data. You can also check the positions. Okay, so the positions where the variants were identified, you can check them out. So we can say BCFTOOLS query -L. Now this one will be -F rather, -F, and then you indicate the position and then /n. And here we just have one chromosome, and then you can just specify the file. and then just run it. So that will give you the position, okay, the positions here. So that's what you need to know. Okay, so let's clear the screen. You can also save the information here, the position here. You can save the positions to a text file. Let's just say post.txt. And then you can even count. I mean, you can just check, or even do a head just to get some of the positions and then the text. So here you can look at the positions in the genome where the variants were identified. So these are things you can explore after generating the VCF file. Okay, so we are good to go. So I believe this tutorial has been helpful, and if you have any comments on how this tutorial can be improved, you can just put it there in the comment section and we can also discuss. If you're also interested in learning how you can proceed after generating the VCF files, you can check my playlist on handling VCF files and then manipulating VCF files using BCF2. So these are things you can do. So that'll be all for this tutorial, and I'll see you in the next session. Goodbye.